Hello all, thank you for joining our presentation. My name is Srikanth Mudigunda. I'll be providing a short overview of a paper titled In-Silico Models with Greater Fidelity to Social Processes, which was submitted alongside my friends and co-authors Santiago Núñez-Corrales, Milton Friesen, Rajesh Venkatachalapathy, and Jeff Graham. As a group, we've been exploring the notion of social primitives, which are parsimonious specifications of agents' memory and behaviors that are sufficient to generate a complex phenomenon of interest. Our past work involved investigations that were either purely geospatial, listed over here, or purely social network based, listed over here, or a combination of these, listed over here. To progress further, we realized that we needed a platform that allowed us to explore these ideas while ensuring that our models had a high degree of fidelity to reality. And the paper that we have submitted to this year's conference, cited over here, is our work in this direction. We realized that we should articulate our motivation based on all the discussions we've had since the last year's conference. And we came up with the following. We want to build models that have a high degree of fidelity to social reality. And this meant that sequencing of actions matters. There is quite a bit of literature in the ABM body of knowledge talking about this. And we also want to build multiple models, what are known as commensurable models, that is, models that are equivalent in their approximation of social reality. Subsequently, we decided that we needed to articulate our goal, and that is to build yet another platform that is scalable. That is, it should allow us to go from a few hundred agents to a few hundreds of thousands of agents, and also several aspects of the environment which are represented. Allows us to have local timekeeping within each agent. That is, we want to have a platform that has a high degree of concurrency. And we also want our platform to be fault tolerant. In addition, it should also facilitate the translation of conceptual models into implementations with minimal friction. My colleague Santiago will next talk about details of what we are planning and how far we have progressed with the implementation of the plan.
In the work at SPEC, we've tried to focus around the notion of social primitives. And by primitive, we don't mean simple. We mean building blocks. And also those building blocks, we assume that they have some representation capabilities of what happens both at the agent level and of what happens at the social level within real individuals, and that somehow the two are linked by these primitives. For SPEC ABM, we have chosen to focus on 6 of them: the spatial primitives, how agents perceive their environment; the sensing primitives, about how agents obtain information without communicating about their environment or other agents; memory, how they store information, how that information is encoded, and how that information may be later used to interact and communicate. Then also we have actions, which are now considered a set of rules of how agents impact their world or other agents. And we have modes of action in this case. And finally, we have composition. Those building blocks, what we seem to observe in reality for social systems is that they're able to be used and composed to generate more complex behaviors. So we've tried to mimic that. So let's look at interactions. Interactions are not sending messages if we open the box a little bit. And we have messages that have an encoding. Therefore, we could have agents with different encodings and simulate the emergence of communication discord, for example, or messages, or agents knowing how they know about other agents, whether by proximity or by some other information-based means. Agents may classify other agents and thereby trigger rules. Or channels. Agents may need to deploy their channels, or they may carry communication channels with them, or they may be just extend across the simulation. Those channels may have noise, and events in the send or receive part may have to wait, or wait or no wait policy, what could be called synchronous or asynchronous communication, but also delayed communication. So let's look at how we achieve these through or what is the implication of concurrency for this rather. So let's see how discrete time ABMS systems try to implement the concurrency aspect. So we have what we call discrete time. Discrete time is a version of logical time in which you have specific instants where updates need to be taken for all the agents often. So there's a bunch of events, and we often have a transformation rule that is based on the agent's behavior, and we obtain a different set of events later in the future. When we look at the distance of the timing, this looks like a square wave. It looks like a step, and this is what we've defined. And that step occurs by means of having a notion of global time called explicitly or implicitly encoded. So it can be simulated by a single processor. It is a discrete simulation step. The ordering of events is often computed, whether it is random or given by priorities. And overall, this is formally equivalent to some other computational abstractions. They may not be as convenient or as AVMs, but somehow there's an equivalence there. Now let's take what we call dense time in a take two. What we mean by dense time is that events that agents undergo, that agents produce, are tied directly somehow to the local time of the computer. So there's a timestamp that corresponds to their reality, to their local observation. Now, we have a series of events that are not as well aligned because they happen to be misaligned due to the operating system scheduler or some other mechanisms that introduce stochasticity. And we still have notion of a transformation, but it is a bit vague. We still see some macroscale observables that resemble pulses, but they're more spread. We still have some certain notion of centrality, or we can still compute when things happen, to say something like this. However, the version of time is local. We could still recover it because there seems to be no overlap. If there's multi-processing, it means that we have some sort of global distributed coordination, and we could still achieve that by simulating it with a discrete single processor. We have a dense simulation step because now we have timestamps and events that happen across different elements, but could be still discretizable with finer resolution. The ordering is not computed anymore, or may not be computed exactly, but one could simulate that ordering with finer resolution still. And it becomes closer to an interacting particle system. However, we still have a distinguishable signal and only a single signal that appears to be similar to a pulse. Now let's do what happens when these signals overlap in dense time. We still have, again, agent events tied to the local clocks. But in this case, we cannot exactly guarantee there's some coordination, and we see the mix between two of these signals. Now, when we look at it, we see a bump in the middle that's smaller than the two, but significant. That is what we call an emergent generative effect. So a surprising event in the system that we did not expect, but occurred not because it was programmed, but because the event emerged due to the concurrency and the coordination and every part of the communication events that were occurring in the simulation. Now we have local time, but that time depends on the agent perspective and on hardware it is running and many other factors. It is no longer easy to convert something that is multi-processing based to a single processor. There's this dense simulation step, and we can no longer sort things out because we have a limit of uncertainty due to concurrency. The simulation is no longer ordered, and to induce an order, it is very expensive. So any ordering will be local, and it is now closer to interacting particle systems. But the important part is that unique timescales arise. Now we don't have only the timescale that we impose as the simulating, as the one you're saying the simulation, but it emerges. So what this means is that somehow the distributed global time implies process supervision. So let's look at what happens when we have only stochasticity induced by the operating system schedulers. So we have a scheduler in any operating system, and usually AVMs implement agents as threads, lightweight or full-grown threads. And sometimes if we only have the ABM but don't interfere with the threads or the scheduling, we don't have a scheduler, we do have agent events that are stochastic in their timing. Now, what happens with the way many of the ABM systems are designed at this point? There's an ABM-induced event ordering, meaning that we have still the same operating system, we have the OS threads, but now what happens with them is obscured because the ABM manages those threads to create sequencing, to create ordering. Then we have the ABM scheduler, and we have the events, but these events are ordered, and they're forced to be ordered. To us, it is a very interesting situation because to one end, it is a more complicated mechanism than just not having the scheduler from the point of view of the architectural design of an ABM. And from the other part, it seems to break the notions of real systems that have social events, where ordering is not exactly induced. And there's this wonderful quote by Oscar Wilde saying that time is what prevents everything from happening at once. And in this case, we are taking if we do an ABM scheduler, we're taking a very strong interpretation of that assertion that may not be exactly real or in concert with reality. So how computer system stacks that ABM have correlate with enabling concurrency and at the same time harnessing or leveraging user knowledge. So let's look at the first part, which we have an operating system and hardware, and we have some AVM systems that are self-contained. You just point and click and design a simulation scenario, and you require little to no programming skills at all. There's another type of scenarios in which we have, again, the operating system and the hardware, but we have system or AVM libraries that allow you to construct simulations. And then on top of that, you have data analysis and visualization tools that allow you to take the outputs from those libraries and create something meaningful. But you can still, with some degree of skill or some programming skill, convert that to a mechanism that people can use without exactly knowing the programming. Now, the more complex case is when you have a bunch of resources that you want to tie in together. First, to build the ABM platform, or to run something, you need to have a parallel distributed middleware implementation. You need to use that to probably write part of the code or use the existing code, but you need to understand the parallelization. On top of that, the data analysis and visualizations tools. And to run these final simulations, you do need at least some basic understanding, for example, of Unix or Linux shells or command line, and they become cumbersome. So there's a degree of power, of computational power, that seems to be inversely correlated with user accessibility. And one of the things that we think is that maybe there's a way to go around it. To do so, we've chosen a different approach. We've chosen the Elixir programming language. It is a direct descendant of Erlang, which was heavily used since the 90s for telecommunication platforms at scale. So this is a language that already scales at 10 milliseconds per event, or can go even lower than that in current architectures. It is based on a virtual machine that has lightweight processes that is natively concurrent, that you can tie these virtual machines together transparently to create large distributed systems without you needing to think about the parallelization, except in terms of fault tolerance and other aspects. But it provides the tools to encapsulate those complicated problems and allow you to concentrate on the science in this case. Now, Elixir also has advantages. It produces a smaller code base by being functional. It is industry grade, but the point here is not Elixir. Elixir is just a good example of what we seek in the end, which is a programming language and a computing stack that allows us to attack the concurrency problem directly. If there's another technology in the future, that will be fine too. So what's the architectonic vision behind what we're trying to do? Is that we have these resources, then we leverage the Erlang virtual machine to do the concurrency part and to tie the resources for us. And we're programming this concurrent ABM implementation called SPEC ABM. What we want is, though, that even if we are the ones that are going to take care of doing the programming, and if people want to contribute, they'll have to learn the language and have to learn the tools. People who are going to actually be using the software would have to write scripts or even do it visually. We're trying to think hard about what that means. And here's an example of the parameterization in JSON. But later, we would like to have this AVM platform running on something that is not an operating system, but a hypervisor, something that is a thin software layer that provides access directly to the hardware to maximize the efficiency of what we can do. So the current working directions, we have two of them. First, the software implementation of the platform. For 2020, we are working on the software design process, and by 2021, we'll be working on the first prototype, and we expect to release it by summer next year. And we also are working theoretically and in an applied manner in cross-platform case studies. So taking some of these classical simulation cases and going through various AVM systems and trying to understand how these AVM frameworks cope with different requirements and what good lessons and what lessons to be improved we find. So this is our team, and we're looking forward to future collaborations, and we remain open for questions and answers. We thank the CSSA committee and the community for allowing us to do this work, and we're welcome to your interventions. Thank you so much.